Okay, in the last video we said that a probability measure must satisfy these three conditions, but that still gives us a lot of latitude or a lot of freedom in terms of how we can choose probability. So you'll see what I mean in a minute. Okay, so they say in most probability problems we need to determine probability of an event, E. So I mean that's usually what you're interested in, knowing what the probability is for some event. The first step in this process is to assign a probability to each elementary event. These probabilities are obtained in one of two ways. So the way we're going to proceed with trying to assign probabilities to an event is first to work on assigning probabilities to the elementary events. These are the elementary points. Okay, so there's two ways to do it. One is by using experimental data. So that means, like, if you don't know, like for a die, maybe, we think we know already what the probabilities for getting a 1, getting a 2, getting a 3, and so on are. But for many cases, we don't have any intuition about it. For example, if I want to know what's the probability that I'm going to get in an accident, in a car accident in the next year, well, I don't have any real intuition about that, but I can use kind of past data, maybe past data for drivers like me, my age, my gender, and so on, and then try to work out the probability from that. So that's called using experimental data. And the other is by logical reasoning and intuition. That's like the probability of getting a 5 when you roll a die is 1/6, right? And that's we just sort of know that, right? Or we have sort of intuition or logical reasoning. There are two different ways of assigning probabilities to the individual elementary events. Like this actually is the right notation for elementary event. And we want to be able to do this, find the probability for the elementary events. So SI means, could be S1, could be S2, could be S3, and we want to know what is the probability for S1, for S2, and so on. In either case, going back up to here, in either case we need to make some assumptions about the problem. It is these assumptions that are based on intuition or past experience. The validity of these assumptions, and hence the usefulness of the value assigned to the probability of E, depends on how well this work fits with future experimental data. Regardless of the method that is used, the probabilities assigned to the elementary events must satisfy the two conditions that follow from the fundamental properties of probability for finite sample spaces. So we have these two conditions that have to be true. So besides these, we have two other conditions that need to be true. And here they are. Each probability must be a number between 0 and 1 inclusive. No, wait. We already said that. Okay, so we already said that. And the probabilities assigned to the elementary events must add up to 1. So for example, if this is the sample space, then these are the then the elementary events would be this one, S1, and this one, S2, and all the way up to SK, because we said there were K elementary events. If you see here, we said there were K. So the last one will be SK. And what we just said is that the other thing is that besides that, the probability of each elementary event must be between 0 and 1. So okay, up above we said that the probability of each event must be between 0 and 1. And now we're saying specifically for the elementary events, they also, of course, must be between 0 and 1, the probabilities for each of them. Additionally, we're saying this, that the sum of the probabilities of the elementary events, this is the sum of the probabilities of the elementary events, must add up to 1, right? So that's like saying if we're talking about rolling a die, and we have the elementary events 1, 2, 3, 4, 5, 6, if we add up the probability for 1 plus the probability for 2 plus the probability for 3 and so on, we have to get 1. In fact, that's what they say right here. Right? Oh no, sorry, it's a little different. Okay, we'll get to that. Okay, so let's continue. Okay, let's continue. When the probabilities are assigned to elementary events of an experiment so that these two fundamental properties of probabilities are met, we call that assignment a probability model for the experiment. Okay, so let's see what they mean. So let's take this example. A six-sided die is tossed and the number on the top face is recorded. So this is the same scenario that we've seen many times already. Thus the sample space is this. If the die is symmetric and perfectly balanced, so kind of ideal die, then the probability model for the experiment would be based on, so if it's symmetric and perfectly balanced, then what we're really saying is that the probability of getting a 1 is equal to the probability of getting a 2 is equal to the probability of getting a 3, 4, 5, 6. Now, just to remind you, we always ask for probabilities of events. So that's why they have to put brackets around this. You know, we don't ask for the probability of 1. We ask for the probability of an event, the event of getting a 1. So they have to put these brackets. So that's the reason for this kind of a little bit ornate or heavy notation. Okay, so what we're saying is that these should all be equal to the same thing. So if they're all equal to the same thing, but we don't know what it is, of course we do sort of know what it is. We know it's going to be 1, 6, but suppose we didn't know what it was going to be, but still they all have to be equal to the same thing. So let's call that x. Now, we said that when we add up the probabilities, they have to sum up to 1, the probabilities of the elementary events. So that means the probability of 1, which is x, plus the probability of 2, which is x, plus the probability of 3, which is x, and so on, has to sum up to 1. So that's x plus x plus x plus 1 equals 6x equals 1, and therefore x must be 1, 6. So we're familiar with that, but they're using these two properties and showing you how to use these two properties. Okay? Now let's go a little bit further and look at this. If the die is loaded, so this means like it's not balanced. Like you might have a die that you've changed it physically somehow, so that you want to cheat with it maybe, and so you've changed it. So suppose the die is loaded or unbalanced, so that 1, 3, and 5 all have the same chance of occurring, and 2, 4, 6 all have the same chance of occurring, but these are twice as likely to occur as these. So 2 is twice as likely to occur as 1, 3, or 5. 4 is also twice as likely to occur as 1, 3, or 5, and so on. Okay? So these numbers are twice as likely to occur. Then the probability model can be obtained like this. So we're saying that the probability of 1 is equal to the probability of 2 is equal to the probability of 3, and let's call that x. But the probability of 2 is not equal to these things, but it is equal to the probability of 4 and 6. So, and we're saying these are twice as likely as these, so this will be 2x. Okay, now we use these properties. First of all this, but this is already, first of all that, and second of all this. That is, if we add up the probabilities for all of them, we should get 1. The probability of this is x, probability of this is 2x, probability of this is x, probability of this is 2x, probability of this is x, probability of this is 2x. So we get actually 3 x's and 3 2x's. And that has to add up to 1. So that means now, this is, if you sum these up, you get 9x equals 1. So in this case, x equals 1/9. So the probability of a 5 is 1/9, probability of a 3 is 1/9, and so on. This one is 1/9, but the probability of 2 is 2 times 1/9, or 2/9, as is this one and this one, as they wrote here. So now we have two different choices. If we have the loaded die, we have these probability assignments, like this, whereas if we have the regular normal die, we have these everything is 1/6. Now both of these are called valid probability models. They're both valid probability models, but they're different, right? So this is one probability model, sign everything 1/6, and this is a different probability model. Okay, so that's what we mean by a probability model. So a probability model is a way to assign probabilities to each of the elementary events. This one, and 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 this one. They all have to be assigned probabilities, but not just any numbers. Like I couldn't assign this to be equal to, the probability of this to be equal to 20, right? What? Why? Because we said that they have to satisfy these two conditions. So first of all of them have to be between 0 and 1, so 20 is not between 0 and 1, so that's already not good. And also they have to sum up to 1. But as long as they satisfy these two conditions, we'll call it a valid probability model. Now, which is the correct model for the die that you have in your hand? That's a different question. So it might be this might be the correct model. Or it might be that this is the correct model. Or of course it might be some other correct model. But so there are many different possible models, but they all have to satisfy a few conditions, these two conditions. So that's why they say, when probabilities are assigned to the elementary events of an experiment, so that these two fundamental properties of probabilities are met, we call that assignment a probability model for the experiment. To assign probabilities to the elementary events, we must access the relative frequencies of these events. Okay. Well, what they're saying here is, if you're not using your intuition, then you have to check the relative frequencies. That means you have to sort of test things from the past and see what happened in the past and then make a guess about what to assign. Now, okay, let's take another look at another example. Example 5. Horses A, B, C, and D are in a race. Assuming no ties, the set of possible winners is this, right? We can either A can win, B can win, C can win, or D can win. John Jones studies the past performance of these records of these horses and decides that A is twice as likely to win as B is 3 times as likely to win as C, and C has exactly the same chance to win as D. Based on John's assessment, which is called handicapping in when you're talking about horse racing, we said that the probability of D and the probability of C are both the same, so we'll call that X. But we said the probability of B is twice as likely as C. I'm sorry, 3 times as likely as C. So that should be 3x. And then we said the probability of A is twice as likely as B, so that should be 2 times 3x, or 6x. Now we use these properties here, and we say that when we add them all up, we have to get 1. So that is x plus 3x plus 6x has to add up to 1. That's 11x equals 1. So x has to be equal to 11. Therefore, the probability of A is 6 over 11. Probability of B is 3 over 11. This is 1 over 11. This is 1 over 11. So you can see that these all add up to 1. And this is called a valid probability model. Janet Jones studies the performance records of the same horses and decides that A and B have equal chances of winning. B is twice as likely to win as C, and C is twice as likely to win as D. So based on her handicapping, we would get something different. So I guess you get X and 2X and so on. Oops, sorry. Yeah, so it's different. So, so this equals 1/11th, and so it's different. So hers are like this. Okay? So I guess hers are different from John's. Both Janet and John have constructed valid probability models. These models are not the same because in the case of horse racing, assessments are subjective, and so the probabilities assigned to the elementary events depend on the handicapper. Okay, so we've been talking now about how to, remember our goal is to learn how to assign probabilities to events in general, but so far we've been focusing on just the simple events, right? Just the probabilities of the S1, the S2, those are the simple events. Okay, now once the probabilities of the simple or elementary events are determined, the probabilities of all other events can be obtained using the following addition principle, which follows from fundamental property 3. Let's go back. What is fundamental property 3? Remember that one? Here. That says that the probability of, for example, E union F is equal to the probability of E plus the probability of F. So if you have union, you can rewrite it as plus. But remember, this is only true when these two events E and F are mutually exclusive. So if they're mutually exclusive, then you can change union to plus. So let's see how we use that to help us find the probabilities of events. So if an experiment has finitely many points in its sample space, remember we said we're restricting ourselves to only finite number of elements in the sample space. So we're not talking about how long you can wait for a bus, because we said that was could be considered an infinite number of points in that sample space. So if you only have a finite number of points in the sample space, so we're restricting ourselves to that situation, then the probability of an event E, where E is going to be some subset of the sample space, right? This is a subset of the sample space. Remember we said the sample space is going to be S1, S2, Sk, so this must be less than K. It doesn't look like it's less than K, but it has to be less than K. So it's a subset of the sample space. So how are we going to assign probabilities to the event, probability to the event E, where E looks like this? We're going to do it like this. The probability of E is equal to the probability of S1 plus the probability of S2 all the way up to the probability of S sub m. Okay, so once we know the probabilities of the elementary events, then if we have E, which consists of a bunch of sample points or elementary points, then we can calculate the probability of E, since we know these. We know this, we know this, and we know all of them. So we just do that. Now the reason why, so let's see. Right. Okay. So why is this related to what was that mutually exclusive rule up there, number 3? Because E, we're asking for the probability of E of this. So that's the probability, but this E can be written as the union of the elementary event S1, union the elementary event S2, union the elementary of union of elementary event Sm. So it's the probability of a union. But if you think about it, each of those are disjoint from each other. So we can change union to plus, and that's where this comes from. The plus, and so on, this plus. Okay, I can't really write here, so I can't say it very clearly, but I hope you understand that. Okay, so anyway, the probability of an event E is obtained by doing this. So they use this language. The probability of an elementary event S sub I is also called the probability of the sample point S sub I. With this terminology, the addition principle states that the probability of an event is the sum of the probabilities of its sample point, which is just what we said right here. The probability of an event is the sum of the probabilities of its sample points. And then they say, well, what about the empty set? Now, the empty set has no sample points, so we can't use this for the empty set. So they say the addition principle cannot be used to obtain its probability. We agree to assign the impossible event, the empty set, a probability of 0. This is reasonable since this event never occurs. Actually, the result that the probability of the empty set equals 0 follows from the 3 fundamental properties of probability of finite sample spaces, and we're going to see that in section 8.3. Alright, let's take a look at this example. I'm going on for quite a long time here, but alright, let's just look at it. A 6-sided die is loaded so that the numbers from 1 to 6 occur with the following probabilities when the die is tossed. The probability of 1 is 2/12, the probability of 2 is 1/12, 3 is 4/12, 4 is 1/12, 5 is 2/12, and 6 is 2/12. So of course all these should add up to 1 if we add them all up. Okay, find the probability of the event E that an even number is tossed. So E is 2, 4, 6, and so the probability of E is the probability, we said, this principle says that to get the probability of the event, you sum up the probabilities of the individual sample points. So we sum up the probability of getting a 2 plus the probability of getting a 4 plus the probability of getting a 6. So that's what they did here, here, and here. It was this, this, plus this, which gives us that. For G, same thing. We sum up the probabilities of the sample points. So we have probability of 3 plus the probability of 6. So it was 4/12 and 2/12, which is 1/6. And the probability of the empty set, we already said that's 0. Okay, I'll stop this and continue.